All right, we're doing more work with our calculator and looking at plotting scatter plots. So basically plotting data and looking at the trends in the data, describing those trends. Is it a strong correlation, a weak one? Is it linear? Is it negative or positive correlation, that kind of thing? And then using our calculator to come up with a line of best fit. So you may have done that in science class. If you've done some experiments and got some data and you've been asked to draw a line of best fit, you may have done it by hand. We're going to use our calculator to do that. And that's something that you're going to use in Math 30, 30 IB for sure, coming up with those, coming up with not just a line of best fit, but a curve of best fit. Maybe it's a sinusoidal, so a sine wave graph, maybe it's an exponential, that kind of thing. So, scatterplots are wisely used to present measurements of two related variables. It's particularly useful when the variables of the y-axis are thought to depend on the variables of the x, the independent. Below is a scatterplot that relates the percentage of car ownership to the household income for people of any town. So it's made up data. We didn't get it in particular. Probably it's a little bit out of date in terms of income, but unfortunately, costs are going up, but incomes are not going up for a lot of people, so maybe it's not that much different. So, take a look here. This is considered a scatter plot. Data was collected and then plotted. So, someone's income, for example, here would be maybe about a little over 100,000, 95% chance that they own a car. Okay. Lower income here, 30%, $30,000, only 55% if I would take transit, right? Because it's difficult to own a car on a low salary. So on a scatter plot, each plot represents a pair of values. The scatter plot shows that 55% of households with $30,000 income own a car. That data points are plotted but not joined. So now we want to look at the pattern of them, and these are some qualities that we can look for to describe the data. So the correlation, is it positive or direct relationships, negative or inverse? Are they scattered? How spread out are they? Is it nonlinear? Maybe it has a curved pattern. Are there any outliers? We talked about outliers last week. Okay, so those are things we're going to look at. So, we don't know what this is representing, but if you take a look at that, that has a strong linear relationship. If you were to take a ruler is a straight line, you could probably match up almost all of those data points in the straight line. There will be a few that are off, but not far off. So it's strong and it's linear, right? So those are two things that we can describe from that. Also, we'll talk about it in a sec, that it's a positive relationship. As the independent increases, the dependent increases. So that's considered a positive relationship. Okay. So here again, this isn't quite as strong, but it is a positive relationship. As variable 1 increases, variable 2 increases. This is a line of best fit. Basically, when you draw one by hand, then you want to make sure you're following the trend and you have approximately the same number of points above the line as below. Okay? So always the first thing to look at is what direction is that trend going? Is it up and to the right? Is it down and to the left? Obviously, you could do a line like this, and students will do that, and they'll say, oh, I counted up. There's this many above it and this many below it. But that doesn't follow the trend of the data, right? The first thing to look for is the trend of the data. Which direction is it going? Then you draw a line with approximately the same above as below, not vice versa. Okay? So, again, we're going to use our calculator, so it will do that for us. But in in science, you might have to do it by hand. Okay, so if the points cluster around a line that runs from the lower left to upper right, relationship is said to have a positive or direct relation. An increase in the value of x is more likely associated with an increase in value of y, and vice versa. The closer the points are to the line, the stronger the relationship. Okay, next one. Looking at the trend of that data, it's going down and to the right. So again, you would draw that, line up your ruler that way, and then check how many above, how many below. Okay, not how many above, how many below by going this way. Okay, so this is a negative or an inverse relationship. Sometimes inverse relationships are more like a 1 over x type of shape, something like this. So you'll see it both ways. But so I often call this a negative because I just keep it within a linear. But it doesn't really matter if it's going that way. As x is getting bigger, variable 1, variable 2 is getting smaller. Okay? But in this case, it's linear. So I would just keep it, say it's negative, but either word works for that. Okay? Then scattered, so looking at how closely they fit a line. That, you can't really tell. Can I draw a line through that or a graph? It's just like a big block of dots, right? So there really isn't a trend that you can tell from it. So if data points are randomly scattered, then there's no relationship between the two variables. So this means there is a low or zero correlation between the variables. Okay. Now this next one, this you can see as x is increasing, variable 1, so is variable 2, but isn't really a straight line. Like I would say it's more almost curved like that if you're trying to think about same number of points above as below. So I would say that that's a non-linear pattern, right? It's not a line, so it's non-linear. So remember we learned about polynomial functions, cubics, kind of have that zigzag. So maybe a cubic curve of best fit. The calculator could actually do that. We'll look at that in a minute. So that has very low or zero correlation in terms of a linear relationship, but it might have a good relationship for a non-linear. Okay, and our calculator will be able to tell us or compare for us using a correlation coefficient R, so that we can compare and see what's the best line of best fit or curve of best fit. Okay, again, spread of data. There's no trend in that. In the first one, widely spread. That's concentrated, but still can't get a line of best fit with that, right? Or a curve of best fit. Okay, and then sometimes you might have an outlier. So this could be a straight line, but this is way far different. Okay? So besides portraying a nonlinear relationship between the two variables, the scatter plot can also show whether or not there exists any outliers. Okay? So now we're going to do some work in our calculator. So there's a bunch of data. So math teachers at Henry Wadsworth are interested if there's a correlation between students marked in 10C and the mark in 20-1. Following data is a random sampling of 33 students. Okay, so now it doesn't matter which one really you put as your vertical, but you take 10C first and then 20-1. So I would make your 10C your independent, your X, right? And then your 20-1 would usually should have some relationship to how you did in 10C. So I would say this is your independent. Okay. Or horizontal axis. I didn't like whatever I did there. So calculator out. This is data, so we're going to go to stat, edit on our list. I'm going to go up and clear off our list there. 10C data, so start entering yourself. Then go to L2 and enter the math 20-1 marks. Okay, so now in the notes here, it goes through all the steps that you do. The step that I like to do first is set up my window. Now you can use Scatterplot, and it will go right to those values to show that data. But I like to see it, like if we're talking about marks, I like to see it in terms of the marks that you could earn, whether these students did or not. So 0 to 100. So I like to choose my own window. But again, you don't have to. It'll prompt you here that you can use Scatterplot. So for my X and Y's, because these are both marks, I'm going to go from 0 to 100. And you can go up by ones, you can go up by tens. The scale really doesn't matter. And 0 to 100. Okay. And then I like to look at the data. So before I even come up with the line of best fit, I want to see that scatter plot. Okay, just the data plotted. If I go to my y equals, just make sure that you don't have any functions listed. It might give you, like, it might not be match your window setting, and then it'll have give you an error. And take a look. Last week we did 2 plots at the same time. I want to do 1. So first of all, I can quickly go up and turn that second one off by deselecting it. Okay. Now I can turn the other one off, but I want to plot it. It's just that in plot 1, I can't remember. I may have done a histogram or a box plot last week, right? If you reset your calculator, these will be off, okay? But I didn't reset it. So to look at the exact setup for plot 1, remember it's second y equals. So anything to do with graphing is y equals or second y equals. And now I can see there that I had a histogram, which I do not want for this. So enter on it. I'm going to keep it on, but the very first type there is a dot plot, and that's what I want. So enter on that. Okay. My list, so my X list is L1, my Y list is L2, already in there. I like to use the little square marking, but you can use any of those. And mine is color, so it'll just be blue. Now if I press graph, it'll show all those values. Okay, notice how there's a gap here because I decided to show from 0 to 100. But if you did that stat plot, then it will fill up more of the screen for you. Okay, so there is a bit of a trend. The better you do in 10C, your marks are going to be equivalent to that. But it's not perfectly linear because there's exceptions to that. Okay, so yeah, and for example, like remember that the screen of your calculator is a rectangle, right? It's not a square. So it may look, just in terms of comparison, this scale is a little bit spread out for 100 marks than this one. So that's why it's going to be a little bit less steep. Okay, but there's my scatter plot, so I can tell that it has a positive relation. As x gets bigger, y gets bigger. In terms of correlation, it's fairly close, but not that close. That's more of a comparison between groupings. Okay, so let's see where we've got. We've got down to here. We've entered it. Okay, so now we want to get the line of best fit. All right, so it tells you if you turn over the page that you want to go to Stat and Calc. That's where we went for our one variable stats, our mean, median, quartiles, standard deviation. Now if you look further, the lin reg means linear regression. So regression means that it's a form of calculating that line of best fit, is a regression line. And it even gives you the slope y-intercept form. So that's the form, when we use this one, that the equation is going to come out in slope y-intercept form. If you look a little further, you'll see quadratic regression. So if we thought maybe it had a U shape, it would be a quadratic. We could use that. Cubic, that zigzag shape. Quartic, that's degree 4. This lin reg is different order, okay? So ax plus b or a plus bx. We're just going to always use the number 4. Then ln, sometimes students get confused with that. That's actually logarithmic regression. We're not using that this semester. So always do the first one, lin for linear. If you keep going, just so you're aware, then exponential regression, power regression we won't do, logistic we won't do, sine regression, so sine, exponential, polynomial, so quartic, cubic, quadratic we'll do next year, okay? We're just doing linear. And then in manual fit, that's a little bit different. Some older calculators don't have those. In any case, go enter on number 4 or press 4. And newer calculators will give you these prompts, okay? Older ones, you'll have to list it. So I think we've done both down here. So if you don't see what I see, then you're going to have to list out L1, comma, L2, comma, Y1. Okay, so if you have an older calculator, that's what you do. If you have a newer one, it prompts you, what's your X list? And notice how I need to change that. It says L2. So I've got to show L1, which is second one. Y list is L2. No frequency on this. And then store regression equation. That means we wanted to calculate the equation and store it in our calculator into y equals. If it puts it into y equals, it's going to graph it. If we don't do that, if we don't put the y1 here, it'll give you the regression line, the equation of it, but it's not going to graph it. And I always like to graph it. Even if you're just asked for what is the line, I want to graph it because I want to see it. So how do we put it into y1? Like we want to put it in there. Well, we go, you got to remember this, and it's listed on here, y bars, so bars for variables. Then see the y variable there, we want a cursor to the right to y variable. And it's a function, right? We learned about functions in Math 10, these are functions. Enter on that, and now choose which one. I'm going to choose y1, and then I want to calculate. So there it shows up like this in an older version of the calculator, and it shows up, you have to put those values into it, and it gives you the A value, it gives you the B value, okay? So I'm just going to write it right down here. Usually we ask you to round to the nearest hundredth when you write it out on your test. So 1.02x minus 14.06. Okay, that's the approximate. This is unrounded, or at least rounded to like 9 decimal places. So now, if I press graph, it'll graph that line, because it puts it into y1. Okay, so it follows the trend, same number, approximately points above as below. Okay, it has a formula for calculating the distance between those points and the line of best fit. Okay, if you go to y1, you'll see that in there. Okay, you'll see that equation, even more decimal places in there. Okay, so that's your line of best fit. Now, when we calculated this, we didn't, there's one more thing that we could do that's helpful in terms of comparing lines of best fit. So if you go down, or maybe it's back up here. Oh, maybe it's on the previous page, sorry. Yeah, actually the first thing listed there is turning on what's called a diagnostic. So to get that correlation coefficient, it's a number that the calculator calculates that can be used to compare how close that data is to the line. And it's used R. The R is used lowercase. Not to be confused with radius or anything like that. It's the correlation coefficient. I think it's called Pearson. It's named after a mathematician called Pearson. Pearson's correlation coefficient. In any case, on our graphing calculators, the TIs, Sophia will have to help you with yours. It might be automatic in Casio to get the R, I'm not sure. But in any case, we can find it in our catalog. So if we go second 0 is catalog, you see a whole bunch of sort of options, programs, or whatever that you can use. You can see absolute value, right? We already can get there a faster way, but this finds other things. So we want to get to a diagnostic, okay, all the way down to D. So rather than just cursoring all the way down, you can actually get there by going alpha D. And where is the d here? It's x to the negative 1. So set alpha. There we go. Register. So alpha, x to the negative 1 gets you to d. And now you can, it just basically skips ahead. So you see diagnostic off, diagnostic on. So enter on diagnostic on, then enter, and it will say done. Now if we do our regression again, stat, calc, linear regression, bars, y bars, function, y1. Same line, right, that we had. Now it gives r squared and r. So r squared is obviously r squared. Oops. Okay, so there, it's r is positive, which means the line of best fit has a positive correlation. If it was negative, it was going down into the right. This means it's going up into the right. And 0.79, so the biggest it can be is 1. If the r value is 1, then the points all lie exactly on the line. Every point would be on the line. So this is okay. It's better to be in the 0.9s kind of thing. Sometimes we would compare r, sometimes we might compare r squared. It's really used comparison-wise between different lines of best fit. But that's your correlation coefficient. So what it does tell you is it's a reasonable correlation, but not, obviously not all the points lie on that line. Okay, and it's positive, so the line is going up and to the right. Okay. All right, so we've got that. That's just a different line. We just gave an example there. Okay, so here, our equation of our line of best fit. Let me just rewrite it here, like we're asked. So y equals 1.02x minus 14.06. And the correlation coefficient to the nearest 100 is 0.79. So here's some properties about it that I talked about. It's between -1 and +1. If it equals 1, there's perfect direct correlation because all the data values lie on the line of best fit. It's -1, perfect inverse or negative correlation. Closer the value is to 1 or -1, so absolute value of r, the stronger correlation is between the two variables, and the closer the points will be to the line of best fit. If r is close to 0, there's not really much of a correlation at all. Okay. All right, so we already did this part, graph it. I like to do that first, so I did it a little bit different order. I graphed the plot first, but there is just notes for you when you're working on these on your own, how to do that. And remember how I talked about here, you can use Zoom Stat if you want. That will just put everything in the, it will sort of eliminate that empty space around the data values. But sometimes I like to have the whole thing, like in terms of marks, then I can tell, okay, there were no marks down in the low, less than 50, there weren't many, right? So it'll zoom in on that. Okay, so let's use our graph now. It says your regression equation can be used to predict Math 20-1 marks for given Math 10C marks. Use your regression equation to predict a Math 20-1 mark if a student receives the following in 10C. So get your calculator out, do your graph, because your line of best fit, that's what you're going to use. You're not using the data points. And if you press trace, the first thing that it will go to, if you press trace, the first thing it will go to is plots. And so you can go back and forth, but we don't want to use the actual data values. We want to use that trend in the data. So cursor down or up, and it will go to the next graph, which is the line of best fit. So now, given different values, right, you can find, given an X, you've got a Y, or vice versa. So we want to know the 20-1 mark, approximately, for a 10C mark of 70. So remember, if you're in trace mode on your line of best fit or any graph, if you punch in the X value, or if you punch in a number, it assumes it's the X value. So an X value of 70, enter on that, and it will go to the point on the line and give you your Y value. So for 70, it's 57.1. Right? Typically, from regular math 10C to regular 20-1, marks go down. Okay? And so that's showing that there. That's why we typically recommend 70% in 10C to go on to 20-1. Okay? So we make sure that you pass 20-1. 60%, so again, if you're in trace mode and you go 60 in 10C, then that's 46, well, basically 47.0. And again, that's why we recommend 70 and 10C. Okay. So you may be asked to use a line of best fit in order to estimate those marks. So what words that we used can be used is interpolation and extrapolation. So did you talk about that in the 10 maybe? I'm not sure. Anyway, interpolation means just finding data values between those that you already know. So like inside, interpolate. So in means between, and extrapolate, extra, outside. It would really be called extrapolation if I said find the mark when the 10C mark is 35%. Okay, and then it would be there because it's beyond the data. Okay, between the data is interpolation. Not that you have to know those words, but just in case. All right. And now you've got some practice. The first one you're going to actually do by hand. Okay. And you're going to draw an estimated line of best fit. All right. And that's it.